Hello everyone, and welcome back to Chem Story. Today we're going to explore a fundamental topic in chemistry, the different types of chemical bonds. Understanding chemical bonds is key to understanding how atoms come together to form compounds. So how do atoms bond with each other? Well, the main driving force is stability. Atoms tend to form bonds to achieve a more stable electron configuration, often following the octet rule. Now let's break down the two main types of chemical bonds: ionic bonds and covalent bonds. First, let's talk about ionic bonds. An ionic bond forms when there's an electrostatic attraction between two oppositely charged ions, a positively charged cation and a negatively charged anion. In simple terms, one atom gives up an electron and another atom takes it. That transfer creates ions, and those opposite charges pull the atoms together. It's that strong electrostatic force that holds the two ions in place and forms what we call an ionic compound. The key thing to remember is this: ions form because both atoms are trying to achieve a stable electron configuration, usually by following the octet rule. Then how do ionic atoms actually form? Let's start with cations. A cation is a positively charged ion. That means the atom loses electrons. This usually happens with metals in group 1 and group 2. Since these metals have just a few valence electrons, it's easier for them to give those up and reach a stable electron configuration. For example, take sodium. It's in group 1. Sodium has one valence electron. To become more stable, it loses that one electron and forms a sodium ion. Now let's look at magnesium from group 2. Magnesium has two valence electrons, and it loses both, forming a magnesium ion. Now let's switch to anions, which are negatively charged ions. An anion forms when an atom gains electrons to complete its octet. This usually happens with nonmetals in group 16 or 17. These elements already have almost full valence shells, so they tend to attract a few more electrons to become more stable. Let's take chlorine from group 17. Chlorine has 7 valence electrons, so to complete the octet, it gains one more electron and becomes a chloride ion. Or take oxygen from group 16. Oxygen has 6 valence electrons, so it gains 2 electrons to form an oxide ion. A classic example of an ionic bond is sodium chloride. As we talked about earlier, each atom forms its ion through electron transfer. Sodium loses one electron and becomes a sodium ion. Chlorine, on the other hand, gains that electron and becomes a chloride ion. Now, since opposite charges attract, these two ions are pulled toward each other. That electrostatic attraction is what forms the ionic bond. And it's not just one pair. In solid sodium chloride, these ions arrange themselves into a crystal lattice, a repeating three-dimensional pattern. That's why ionic compounds like this have really high melting and boiling points. The structure is super stable, and it takes a lot of energy to break it apart. Now, let's talk about the force that actually holds ionic bonds together: electrostatic attraction. This attraction between oppositely charged ions follows a basic principle in physics called Coulomb's law. So what does Coulomb's law say? Well, the greater the charge on the ions, the stronger the attraction between them. And the closer those ions are to each other, the stronger that pull becomes. In simple terms, higher charges and shorter distances make for stronger ionic bonds. You'll get a better feel for this once we look at the formula. But even without the math, this idea helps explain why some ionic compounds are more tightly held together than others. Now let's talk about covalent bonds. Covalent bonding is the most common type of bond between nonmetal atoms. Unlike metals, nonmetals don't easily form stable ions just by gaining or losing electrons. So instead, they share electrons to satisfy the octet rule. This type of bonding is especially important in organic chemistry. In fact, covalent bonds make up the entire backbone of organic compounds, and they're the reason complex molecules, like proteins and DNA, can even exist. So yeah, without covalent bonds, life as we know it wouldn't be possible. Then, how exactly does a covalent bond form? Well, each atom brings in one unpaired electron, and together they form a shared electron pair. By sharing that pair, the atoms stay connected, and that's what we call a covalent bond. This shared pair of electrons helps each atom reach a stable configuration, usually following the octet rule, just like the noble gases. For example, let's look at water. Oxygen has 6 valence electrons, and it needs 2 more to complete its octet. Hydrogen has 1 valence electron and needs just 1 more to be stable. So what happens? Oxygen shares 1 electron with each hydrogen atom, and that forms 2 covalent bonds. Now, here's something important. Covalent bonds are strong and directional. They hold specific atoms together in a defined shape, unlike ionic compounds, which form large, repeating lattice structures. All right, now let's take a look at the different types of valence electrons. To really understand how covalent bonds form, we first need to know which electrons actually get involved in bonding and which ones are just along for the ride during chemical reactions. By breaking down the roles of each type of electron, we can get a much clearer picture of how covalent bonds work. So let's start with unpaired electrons. Unpaired electrons are valence electrons that are free to form bonds. They're the ones that actually want to pair up, and that's what makes them available for covalent bonding. The number of unpaired electrons usually tells us how many covalent bonds an atom can form. But keep in mind, this only applies when we're talking about neutral bonding situations. Now let's talk about another important type of valence electrons, lone pair electrons. Lone pair electrons, also called unshared or non-bonding electrons, are a bit different from unpaired electrons. These are paired electrons in the valence shell that don't participate in covalent bonding. Instead of forming bonds, lone pairs play a major role in how molecules behave. They influence things like molecular shape, polarity, and overall reactivity. So understanding the difference between unpaired electrons and lone pairs is really important if you want to predict how atoms bond and how molecules will interact in chemical reactions. This table shows the electron configurations of key atoms, including hydrogen, carbon, nitrogen, oxygen, and the halogens. And like I mentioned earlier, the number of unpaired electrons tells us how many covalent bonds an atom can form with other atoms, so keep that in mind as we go through the table. Now, let's talk about the different types of covalent bonds. Covalent bonds form when atoms share electrons, but that sharing isn't always equal. It depends on the electronegativity difference between the two atoms. If the difference is small, between 0 and 0.4, we call it a nonpolar covalent bond. Electrons are shared equally, like in carbon-hydrogen, or diatomic molecules like oxygen and nitrogen. If the difference is between 0.5 and 1.7, it's a polar covalent bond. Electrons are shared unequally, so one atom gets a partial negative charge, delta minus, and the other gets a partial positive charge, delta plus. This happens in water and ammonia. But if the electronegativity difference is large, one atom fully takes the electron, and that forms an ionic bond. Like in sodium chloride, where sodium becomes Na+, and chlorine becomes Cl-. All right, let's wrap up. Today we explored the two main types of chemical bonds, ionic and covalent. We saw that ionic bonds form when electrons are transferred from one atom to another, creating oppositely charged ions that are held together by electrostatic attraction. These are common between metals and nonmetals, and they form strong, lattice-like structures. Covalent bonds, on the other hand, form when atoms share electrons to achieve stability. They're especially common between nonmetals and form the backbone of most organic molecules. Understanding how and why atoms bond, whether by giving, taking, or sharing electrons, is the key to understanding all of chemistry. That's all for today's lesson. Thanks again for joining me, and I'll see you next time on Chem Story.